Okay, good morning everyone, and welcome to the April 2017 Soils Network of Knowledge webinar. Now I'd like to introduce Terry Rose, who's from Southern Cross University up here in Lismore. Terry's an agronomist who has a strong interest in the mineral nutrition of crop plants, particularly phosphorus, and the development of crop cultivars with tolerance to nutrient deficiency stress. So prior to working with Southern Cross University, Terry worked in both the public and private sector. He was an extension agronomist with New South Wales DPI in both Wagga and the Hunter Valley, and has worked with a private company in the UK. And he's also worked in the not-for-profit sector with Plant Health Australia in Canberra. So today, Terry's going to talk about some of his more recent work at Southern Cross University, looking at the efficacy of nitrification and urease inhibitors on nitrogen fertilisers in the wet subtropics.
Thanks, Abby, and good morning, everyone. It's interesting that I've called this topic nitrogen in this wet subtropics because our climate has been quite true to type of late, and it kind of highlights the difficulties we face. So we had 2 months ago, we had crops that were well and truly drought stressed and some that wouldn't even recover from that. And following that, a lot of them went underwater and they just got their heads back out of the water, and now they're fully underwater once again. And so the wet subtropics is kind of unique in that way, in that we don't have a nice uniform rainfall pattern. We face both drought and we face deluge, and that makes nitrogen management pretty difficult. So why are we interested in the nitrification and urease inhibitors, or any nitrogen fertiliser product really, that can enhance the amount of nitrogen from the fertiliser that the crops take up? The main reason is because it's estimated that about 50% of the nitrogen applied in our region anyway. So I'm based on the north coast of New South Wales, but there's probably regions in southeast Queensland that are quite similar, but we lose about 50% of the nitrogen applied, and that's the results from the last review paper that was conducted in 1994. So the main crops we grow are sugarcane, or main field crops I should say. There's a lot of horticulture as well, but most of our studies have been with broadacre crops. So we've got sugarcane, which is often grown in rotation with soybean. Then we've got tea tree, which is in the far right, and that's actually an inter-row crop of mung beans you can see there that we were trialling to see if we can fix nitrogen and supply the main crop with nitrogen that way as opposed to fertilisers, but that's a different story. And more recently, we've been toying around with rice in amongst the soybean and cane rotation. So that's a brief summary of the nitrogen cycle. The main losses that we get in the subtropics here tend to be through leaching of nitrate. And it's these big events or even just a good storm following any application of fertiliser that tends to be the main driver. However, we also can get, and it's estimated around up to 20% losses as denitrification in some of our clay soils. We also have, we can have, especially with the use of poultry manure, we can get ammonia losses, and we also get some nitrous oxide emissions, although while they're important from a greenhouse gas perspective, they're not generally a huge part of the nitrogen budget. So in order to address these problems, there's a fair few products on the market at the moment that attempt to slow the supply of nitrate, or they try to reduce the formation of a large pool of nitrate in the soils. And it's the formation of nitrate, or these pools of nitrate, that are susceptible to either denitrifying and causing losses as N2O, or then further to N2, or they're susceptible to leaching. So there's a number of products out there. There's urease inhibitors that inhibit the first step. So if you apply urea, it needs a urease enzyme to convert it into ammonia, and you have urease inhibitors act here, and then once it forms ammonium in the soil, which can actually attach to the soil because they have cation exchange capacities, so it's less likely to move anywhere than nitrate. If you can hold the fertiliser in ammonium form, that's quite beneficial. So the nitrification inhibitors work on this, and they try and hold it as ammonium and stop it turning rapidly into nitrate. And then you have polymer coatings and various kinds of coatings on a range of products that simply try to slow the release of urea into the ammonia stage as well. So we've conducted a fair few trials over the last few years in the northern rivers, mostly looking at nitrous oxides, but also some agronomic studies just looking at nitrogen efficiency. And I'll show you the results of some of those today. Now, we used commercial products for these trials. We didn't use the actual inhibitors themselves. We just went out and bought off the shelf or were given by fertiliser companies products that are currently sold to farmers, and we tested them to see whether they could reduce nitrous oxide emissions or whether we could put on lower application rates and get the same yields. So from the literature, we sort of expected that we might get up to 40% reductions in nitrous oxide emissions by using these products, and that's from a couple of recent meta-analyses. But when you look into those meta-analyses, most of the data are from temperate regions, and we didn't find much from the subtropics. So we were pretty keen to see whether our results were the same or whether we sort of contrasted what was reported in those meta-analyses. So we used static chamber methodology, which is essentially whacking those chambers you can see on screen in the field. You have the lids off most of the time when you want to sample nitrous oxide. You come in usually between 8 and 11 in the morning, put the lid on, take a sample with a syringe, put it into a vial and bring it back to the lab, and our samples were analysed at Wollongbar DPI. You then come back exactly 1 hour later, and take another sample, and the nitrous oxide that's fluxed out of the soil in that time will be within the chamber, and as long as you pump it a few times to get the air mixed inside, you can get a pretty representative sample of the gas composition in there, and we find out what nitrous oxide fluxes there were. So this is one of our trials on a rice crop. That we've also done work with sugarcane, but to be honest, rice is a lot more easy to manage, and anyone who's been into sugarcane paddocks and tried to sample will appreciate why. So we sowed a local cultivar, Tachi Minori, that's sown by most of the farmers around here. We threw on 80 kilos per hectare of nitrogen, and the reason we used that rate is because trials over the past few years have shown that's roughly about the rate that gets us our maximum yields. Obviously that depends slightly on the paddock and the history, but around 80 kilos seems to max us out, and that gets us 5 to 7 tonnes a hectare of rice. So the previous crop was sugarcane, and there'd been a 7-month fallow. So over here you can see the nitrous oxide production across the season. So we go from January up to May when harvest was, and you can see it was, relatively speaking for our area, reasonably dry in February, March. Then we had a big rainfall event in April, and then another little one in May. Urea was the control. Then we have urea DMPP, which is actually the commercial product NTEC, and then we had a blend of the two. So because a lot of farmers say the price of NTEC is prohibitive, we split. We had 50% urea, 50% NTEC urea to see what results that gave. So the fluxes have been modelled by Steve Morris, the biometrician at Wollongbar, and it's much easier to see than if we just presented raw data where there's a lot of noise because measurements vary within a couple of metres in a field, and so you get a lot of error associated. But this graph shows the urea in the black line, and then the grey area around it is the LSD, if you like. So it's at P equals 0.05, anything outside of that grey area is significantly different. So you can see in this main flux period here, so fertiliser was applied back here, then you get the big flux following the application and a bit of rainfall, and during that time, the NTEC and the NTEC plus urea, the 50-50 blend, were actually significantly lower in that flux period. Beyond that, there were very little emissions. So it pretty much after that first month, nothing happens. Even with these big rainfall events down here, there's no nitrogen left in the system to actually turn into N2O. So that looks promising back here, but then beyond that, nothing happens. So if we go over to the total seasonal emissions, when you analyse it, you find that there's actually no difference statistically. So urea gave off 0.42 kilograms of N2O per hectare, and as you can see, as a percent of the total amount of nitrogen applied, it's not huge, but as a greenhouse gas, it is significant. But there was no difference across the season, and that's simply because you can see the error over here, and it's all this tail where not much is happening. The error created here means you don't find significant differences. But this little part of the curve here was quite promising. So in that early period, it did look quite good. The next season, we grew the same type of rice, different paddock, 80 kilos of N again. And this time, because the blend appeared to have a similar trajectory as the N-Tech in the first one, we used urea. We used urea DMPP, which is the Intec, and this time I threw in a polymer coat to see what happened. So in this season, we had a big rainfall event up front, another one about a month later, then a relatively dry period after that. So we actually had 2 flux events here. After the first rainfall event, emissions were quite high, but you can see the urea and the urea DMPP, which is N-Tech, they're pretty much sitting on top of each other. So there was no difference between those two. This line down the bottom is the polymer coat. So the polymer coat urea, it wasn't significantly different at P equals 0.05, but it was pretty close. So in that main flux event, the polymer coat looked like it may have been effective. Beyond that, they tend to merge and nothing's going on. So again, if we come over here to look at the total amount emitted across the season, there's no difference. And the emissions were roughly the same across the season as the year before. So one season, the N-Tech appeared to do pretty well, and the next season it mimicked what urea did, and the polymer coat urea seemed to have some efficacy in reducing nitrous oxide emissions. So that's 2 of our trials. We had 3 other ones over the past couple of years. We had a repeat with the N-Tech and the polymer coat on a peat soil. The last 2 trials I showed were on a fairly clay profile that gets extremely boggy after a big rainfall event. And sorry, this is in 2012 and 13. It wasn't in 2015, 16 there. We had no significant difference in the main flux period there. So the lines sat on top of each other, and across the season, no significant difference. Another one last season where we tried N-Tech, we tried polymer coat urea. We threw in green urea, which has the urease inhibitor NBPT. And we tried a black urea, which is a carbon-based product, and they're all sold commercially around the place. This is back on the clay soil. Again, the curves sat on top of each other, even in the main flux period, so no difference there and no difference across the whole season. Same treatments on the peat soil last year and exactly the same result. So no difference in that peak flux period and no difference across the season. So all in all, there's a fair bit of variability across our trials, and there was no clear evidence that any inhibitor products can actually reduce seasonal emissions from a statistical point of view. We had 1 and possibly 2 trials where there was a hint towards reduced emissions in the peak flux, but then 3 trials where absolutely nothing happened. So moving on from those nitrous oxide trials, and probably of more interest to growers, is what happens with grain yields. So in all our trials, at the rate of 80 kilos per hectare, there was no difference in grain yields. However, you wouldn't expect there to be, because we've just put on the rate of urea, which is the control that we expect to get maximum yields. So it would be silly to expect that giving more nitrogen to the system is going to increase yields. On that note, if you look at recent papers in the literature, and there's 5 have come out in the last few years, but I'm going to pick on Abelos. They all conclude the same thing. They all look at studies and find very few yield increases or very little yield increase from either DMPP, that's the one used in Intec, or NBPT, the one used in green urea, or another nitrification inhibitor called DCD. So they find you get these tiny yield increases, even though you do get up to 40% reduction in nitrous oxide. However, if you actually look into those studies, they're all conducted or most of them are conducted at a single rate of nitrogen, and that single rate of nitrogen is usually the recommended rate for that region. So I would argue that those papers are somewhat flawed in that you shouldn't expect a nitrogen response if your control is the rate of nitrogen that's non-limiting. So bearing that in mind, what is needed to actually test these products is a nitrogen rate response trial, where you try 5 or 6 rates so you can derive a fertiliser response curve, and you test that against urea. Now, to the best of our knowledge, the only published studies that we've found using N-Tech that have actually gone and bothered to do the work and the reason presumably is because it costs a lot to run such trials, is some work on sorghum up in Queensland. And they had 5 trials over a couple of seasons, and they didn't find any large response, or they didn't find that you could reduce the amount of NTEC fertiliser applied and get the same yields as urea. But that's one study in the whole of the literature that we found, which was quite surprising given what a hot topic it is. So we ran our own. This trial was on the clay soil that we ran the rice nitrous oxide trial on in 2015-16. We've shown the data here are not means, they're actually the individual replicates. There was 3 replicates, and we've got the black dots are our control, urea, and we had 6 application rates, including a 0 N control. But you can see the 0 N control still yielded 3 tonne of rice per hectare. And then we've got in the blue was NTEC. We actually ran this with 4 other products as well, but I'm just showing you the NTEC versus urea because essentially we got the same result with all of them. So it's a reasonable amount of noise, but it's the same sort of noise that you see in most field trials. What we have in the black line is the fitted curve for the urea response. The blue line is the fitted curve for the NTEC response. The dotted lines, the dotted black line, is the 95% confidence interval for that fit for the urea, and ditto for the 95% confidence interval for the NTEC. And so you can see the confidence intervals overlap, and there's no significant difference in those response curves. Now, even if you get picky and decided that point's too high, this point's too low, and you toss them out, which we didn't in the end because we had the biometrician look and he said, no, they're not outliers. But even if you do, and we toyed around with it, you don't get a huge difference in the response, the shape of the response curve. So from this season, what you conclude is the products behaved exactly the same, and you couldn't reduce the rate of the inhibitor product and get the same yields. And that in that trial was the same for green urea, for black urea, and for polymer-coated urea. We couldn't reduce the rate of any of them and get the same yields compared to urea. So that's only one season. We've got another trial in this year looking at the same thing, and I'll probably throw in a couple more in the next few years because given the lack of data out there on it, I think it's time we started, even though it's expensive, running proper trials to see whether these products can be used at a lower rate. So one of the reasons we thought we might be getting different results to the literature, at least for nitrous oxides, while we aren't seeing the big drops in nitrous oxide, and possibly why we didn't see a response last year in our rice trial, while we couldn't use less, we thought maybe the warm temperatures of the subtropics are different to a lot of the published studies from temperate areas in that it causes there's a different dynamic between the bacteria in the soil, the microbes in the soil, and the inhibitor you put on. So here's some data. Here's some data from a paper from Delhi Chen from 2010, where they've done some incubations, and an incubation is where you just put a bit of soil, a known amount of soil, in say a test tube or a falcon tube. You put in a known amount of fertiliser and you put it in the dark at a given temperature, and over time you can measure changes in anything, but in this case they measured changes in ammonium and nitrate production. So this is ammonium, and this is at 5 degrees, so this is at a cold temperature. So what happens is you've put the fertiliser in after day 0, you get production of ammonium up here, and it stays pretty constant and doesn't drop off. And the reason presumably is because it's quite cold and the bugs aren't doing much, so they don't convert it into nitrate. And this is at 40% water-filled pore space. 60% water-filled pore space is sort of optimum for nitrous oxide production. But even at 60%, not much is going on. When you increase the temperature to 15 degrees, the urea treatment, which is this black one, after about 28 days, starts to convert to nitrate. Well, you can't actually say it from this graph. All you can say is the ammonium is disappearing. But if you go over to the other graph over here, which is nitrate, they match each other quite well. The nitrate starts to go up. The products, so the triangle is DMPP, that's NTEC. This other one's called NSERV, and that's is the basis of a lot of products sold over in the US at the moment, although they are creeping into Australia as well. So the NTEC can hold it as ammonium. The urea starts to turn to nitrate. As the temperature increases again, after 7 days, the microbes quickly start turning the urea from ammonium into nitrate over here. So you get this big increase in nitrate, and that's what we're looking to avoid. So over here at 25, if you can hold the nitrogen in the form of ammonia for this extra from 7 to 42 days, then it's not susceptible to leaching. It's less susceptible to forming nitrous oxide, and the plants can still get it, and it'll adhere to the soil cation exchange. So that is a good outcome. Interestingly, at 60% water-filled pore space, these guys found that the NTEC starts to drop off, but it was better than, the NTEC starts to drop off, whereas the NServe, which is the one that forms the basis of a lot of American products, doesn't drop off. Anyway, onwards to our data. So we use some soils from around here. We've got the clay loam soil, or it's clay loam topsoil. It gets pretty clay beneath that, with a pH of 5.6, 2.3% carbon from down in our rice trials. So we did the same. We incubated them in falcon tubes with 15 grams. We added a big wallop of fertiliser N because we actually added the product, the fertilisers as bought from the shop. So we actually, when I say we, it's a royal we. My technician weighed out individual grams of fertiliser. It took him 3 days to set this up. He got the exact weight of all the granules and found granules of the same weight and added 1 to each, and that was a rate of 400 kilograms of N, which might seem high to some people who aren't from around here, but it's not that high. You know, you can get 200 to 300 kilograms of N thrown on a big cane crop, so it's not that unrealistic. And we incubated them at 3 moisture contents at 30 degrees instead of 25. So let's start with the nitrate production over here. And we've got 40% water-filled pore space, where usually not that much happens, 60%, which is optimum for nitrous oxide and a lot more action. And we put 90% in because reasonably frequently our topsoil can be up at 90% or above. Whenever we get a decent rain event on these clay soils, it'll stay for a few days quite saturated. So we tried that as well. What you can see is, and here's so urea is this little guy, green urea, which is the NBPT, is the circle, and then the NTEC is the square. But regardless, not much difference. You come up to 60%, not much difference. Now the NTEC here seemingly has a bit less nitrate production. We're going to check that, because I would have expected if it's going to start separating here, then when the nitrate started to form back here, that it should still have been active. So that's a bit of an anomaly that we're going to repeat and see if we get the same result. Over at 90% water-filled pore space at 30 degrees, they're all the same. So we didn't see the same results as the Chen paper. What we hypothesize is that A, we're at 30 degrees, not 25, so the bugs are a lot more active, and B, we think our soil is probably, or has more labile carbon and food sources for bugs, and is just a more biologically active soil. So when you put these fertilizer products in, it's the competition. The inhibitors are trying to inhibit the microbes that can do nitrification or have urease activity, while the rest of the bugs are just trying to eat these products and use them as a food source. And we suspect that at the rate of inhibitor used on these products, in our soils that are highly active, and in summer crops where the soil temperature is warm, the soil microbes can destroy and eat the inhibitors before the inhibitors can act on the bugs that do the nitrifying. The other reason we think that our soils might be more active is because if you look at the soil ammonium concentrations, they don't drop off. And so over here, let's look down here at 90% pore space. Even while nitrate is increasing over here, we don't see the same drop off in ammonium over here. They're not concomitant. What that suggests is, as ammonia is turning to nitrate through the nitrification process, bugs are also active on soil organic matter and are turning organic nitrogen sources into ammonium. And so that in itself, when you look at these results compared to Chen's results here where it drops off, suggests that we have quite an active soil. So that's our current hypothesis as to why we may not be getting the results, and we are going to continue looking at different soil types and look at some different concentrations of these inhibitors to see whether that is the reason. So in summary, we didn't find any significant lowering of seasonal nitrous oxide emissions consistently in 5 rice trials. Both NTEC and Polymer Coat showed some evidence during peak flux events in one season each that they could reduce nitrous oxide fluxes at that time, but it didn't translate into lower seasonal emissions. And we need to better understand what is happening with these inhibitors, whether or not we need to increase the concentration of the inhibitors, whether we need to try new inhibitors. I'm not sure, but we need to try and work out what's going on so that we can improve it. So our current data suggests that given the extra cost of the fertilisers with inhibitors, they don't appear economically valid based on our current trials, but we obviously that was just a few seasons, and we need to do more work to see whether in some seasons they can be used at reduced rates to produce maximum yields. And finally, I say it's not good enough to simply go and tell farmers, that our trials show they're ineffective. We actually need, given that we're losing 50% of our nitrogen from fertilisers to the environment, and we live in a pretty environmentally sensitive area, we actually need to do some hard work and find products that do work. Otherwise, we're going to find ourselves as an agricultural industry under a lot of pressure. And I dare say it's the same in Queensland, where you've got crops growing near the barrier reef. The social license to farm is going to come under pressure. So it's not good enough to say they don't work. We actually need to work with companies and find products or modify products to make them work, and make them work at an economically viable cost to farmers. So I'll leave it there. Thank you for listening, and I think Abby has a way that you can send any questions in. Thank you.
Thank you very much, Terry. That's fantastic. As I said, we've got now time for questions. Steve Kimber.
Yeah, that's a great presentation, Terry, for quite a complex story. I think you're really pushing things uphill because you've got so many changing conditions and mechanisms that vary with soil moisture and temperature that, with 1 or 2 trials, it's very difficult to show what's going on. And also making a comment on the polymer coat, I think there's a need for 3 or 4 different levels of resistance or release resistance for the fertiliser, so you get some sort of coverage of nitrogen needs right across the season.
Yep, I agree with that, and I think that's something that's been missing from polymer coat trials at the moment too, is different blends. Even a urea, 25% urea, 75% polymer coat, or as you say, there's different polymer coats that have a different release pattern. Trying different blends, I think we need to do it. The problem, as always, is that when you start running decent sized replicated field trials and you start mixing things up, it gets expensive. That doesn't mean they don't need to be done. They do, but you need funding to do it. And it'd be nice if this sort of work was prioritised, I think, because there's a lot of study, a lot of the nitrous oxide stuff out there is fairly pointless for growers. It doesn't represent a big NLOS pathway, and I think, as you say, a lot of these product combinations need to be tested, and they need to be tested in an agronomic sense over multiple seasons, so we can actually try and work out in what seasons they might be effective.
If a price was put on nitrous oxide emissions, that'd change the economics of it too.
This is true. Yep.
There's a few other questions that have come in that are typed, so I'm going to read those out. Justine Cox is interested, Terry, to know what the individual company's response to your data has been.
So far, I've only presented parts of the data at a conference, and I've flicked off some of the results to one of the companies, but it's taken me until about a month ago to actually get all the data together. And there's actually a couple of other data sets that I haven't finalised yet that I want to put all together before I actually go and talk to them, because I think it's much as they were interested to see the preliminary data and sort of see the data as it was coming in, I think for a proper discussion, I'd like to take all the data we've got, which is all the field trials, all the incubations with different soil types, and look at it as a whole. So the short answer is I haven't actually shown them the full data sets yet, but I intend to, and hopefully we can have some interesting discussions.
Okay, thank you. Next we have a question from Rob Norton, and he said, have you got any comment to make about the losses of nitrogen as dinitrogen?
Good question, Rob, and it's something that we are just starting to set up some incubation studies now looking at, following some work from David Rawlings up at QUT, where they looked at some dairy soils where they were quite puggy, and they were getting, I think it was 20+% losses as dinitrogen in those soils. That was irrigated dairy soils. We suspect, and particularly given the weather events we've had this year, where even without these giant flooding events, if you get a good storm with 50 or 60 mils in it, a lot of these soils, the topsoil gets wet enough, we think, to fully denitrify. So I don't have any data on that at the moment. I apologise, but we are setting up incubation studies at the moment to actually work out with our soils when it might occur, and then if we look at some historical rainfall data, we can then try and model when we think it might have occurred and try and get some idea of what the losses might be. But if the data from Queensland is anything to go by, I think we will be getting reasonable amounts of dinitrogen losses, more than ammonia losses, put it that way. I don't think we're losing much as ammonia. We've got fairly acid soils, and a lot of the guys put the nitrogen into the ground anyway. So I think dinitrogen losses are going to be a much bigger loss pathway than loss as ammonia gas.
Thank you, Terry. And further to that, I think I just heard you mention some work that was done in pastures. Is that right? Neil Griffith was wondering if you have looked at the pasture work that Warwick Doherty has done that seemed to show similar results. He said not enough yield to cover the extra cost of the product.
I haven't seen that. I've had a few people talk to me about that, but I haven't actually seen any of the data in either a report or paper yet. But that's interesting that there was similar results, that you can't lower rates, or the degree to which you can lower rates doesn't justify the cost at present. Yeah.
And further to that, Robert Gees also said that they've got similar thinking to how things are working in southern pastures, but they would like better efficiency of nitrogen used. So it's obviously a common issue. Did you want to comment on that? Or?
Yeah, I will, because you hear of, at a few conferences I've been, you get a few academic types saying, oh, it doesn't work, this is rubbish, blah, blah, blah. But I think Robert makes a good point. The fact is we're still having low efficiencies of nitrogen use. So it's not good enough to just poo-poo things and say they don't work. The reality is we actually need to work out what's going on and keep working to find products that are economically viable for farmers to use, that actually do increase the efficiency of use, because otherwise I think we're going to get in strife at some point, particularly in environmentally sensitive areas where the locals aren't going to put up with poor water quality. And so I think we have to keep plugging away and find ways to increase the efficiencies.
Yeah, good point, I think. Now a slightly different question from Phil Hurst. He said with the temperature regimes, is it worth considering soil temperatures over the year and therefore adjust the application of fertiliser according to that?
In the end, the fertiliser rates you're going to apply should be based on trials, nitrogen rate trials over many seasons for that crop in that season. So I don't think, for example, say there's a bit of barley grown out towards Casino from around here, I don't think there'll be any way we can say, okay, soil temperatures are going to be lower over that winter period and we can change our nitrogen rates according to that. I think we simply need to go and do nitrogen trials out there, rate trials, and come up with recommended rates that are suitable for that crop in that season. I think that's a better way to go about it. Even though what you're saying is probably true, we might find better efficiencies because of that during those seasons. But in the end, I still think to come up with valid recommendations, you've just got to run the trials get enough data to do some models, and then possibly even run an economic model over the top in the same way that state governments have been doing it for years and years. I think that's still the best way to do it.
Okay, thank you for that, Phil. And Rob Norton says, he's given a comment on the value of inhibitors, is that they generally have a short residual time, maybe less than 40 days, and they will only be effective if the loss process is operating at the period when the inhibitor is active, which makes sense. And this is difficult in cane as the opportunity for interventions is limited and the duration of crop growth is long. So you probably only get one shot for it to work. So thank you very much for that comment. Did you want to say anything?
No,
that's it in a nutshell.
Point, Rob.
Okay, and I will take this opportunity to thank Terry. I took the liberty of putting his email address up there on that slide that you can see. So if you do have any other questions that occur to you afterwards, you could forward them there. And thanks very much, Terry.